Okay, as promised, we're going to do triple integrals using cylindrical and spherical coordinates. And here's how it's done, right? So these are the Fubini's theorem version for cylindrical coordinates and for spherical coordinates. And the thing you have to be careful of is the dv, right? It's in rectangular coordinates, of course, dv, right, was just, dz, dy, dx, or some permutation thereof. Dx, dy, dz, dy, dx, dz, doesn't matter, right? Right? So it's a length times a length times a length, which is, a volume, right? Cubic meters, right? So, yeah. So that's rectangular, right? This was for rectangular as a review. So for cylindrical, remember, cylindrical is a lot like polar coordinates. In fact, it is polar coordinates in 3 dimensions. In 3 dimensions, you just add the z-axis, right? The z-coordinate. So no surprise that dv is not going to be dz dr d theta. That doesn't have the right unit, right? That's not the right dimension. It's, right, this would be an area. Right? Remember, an angle is not a length. An angle is just a number. So it's a length times a length times a number. It's an area, not a volume. So that's why we need the r here, right? It's the same as it was in polar coordinates when we did r dr d theta, but now we also need the z, the dz here, right? Okay. So that's cylindrical. Spherical gets even more complicated, right? So these are the conversions for spherical coordinates. But now the dv involves this whole mess here, right? It's obviously not just d rho, d phi, and d theta, because this is not even an area. This is a length. So you have a volume equals a length. That's not going to work, right? So to fix that, of course, we multiply by rho squared sine phi. Now, the rho squared, that's an area, right? That's a length squared. And then the d rho is a length. So that gives you area times length. That gives you a volume. All right, so the units work out. However, that doesn't necessarily explain then where does this sine of phi come in? Yeah, so that would take a little more explaining. And I think I'll do that in the next video. Yeah, so I will explain this a little bit later. This is what's called the Jacobian for spherical coordinates. That doesn't mean anything to you yet, but it will in the next section. So don't worry about that yet. For now, just assume that this is where, whenever you're converting to spherical coordinates, whenever you need a dv, right, if you're doing dz, dy, dx, and you want to change to d rho, d phi, d theta, you have to multiply by this rho squared sine phi. In the same way that for cylindrical coordinates, you have to multiply by r. And if you forget the r, or you forget the rho squared sine phi, all I can say is that you're going to get the wrong answer. So please don't forget it. It's on your formula sheet, so whenever you need to switch to cylindrical or spherical, look at the formula sheet and remember, oh yeah, I need the rho squared sine phi, or I need the r. All right, so that's the conversions. Let's just do an example. Okay, so find the volume of the region Q. This is a solid region in space, right? X, Y, Z. And x squared plus y squared is less than or equal to 25. And z is between 0 and 12. Okay, so we can set this up as a triple integral of just one dv. And so what is this? This you should recognize. 1, 2, 3, 4, 5. It's just a disk of radius 5, right? It's everything inside the disk. Right? It's basically saying r squared is less than or equal to 25, or r is less than or equal to 5, right? So of course we could have just said r varies between 0 and 5, but that would be too easy. And z, of course, is the same in cylindrical as it is in rectangular. So z is just between 0 and 12. So Right, so what is Q here? Q is just the cylinder of radius 5, right, and height 12. Sorry for the sloppiness here, but yep. Right, we're going from z equals 0 to z equals 12. So the height is 12, whatever, 12 units, right? So yeah, we don't need calculus for this, right? You probably know the formula, right? But in some ways, we're just going to derive the formula here, right? Yeah, and so to do this in rectangular coordinates would involve calculating the following integral here. Right, so z, I guess z would be first, right? So z goes from 0 to 12. Actually, it doesn't matter because this is just the constant, right? dz. But y goes from, let's see, negative square root of, I might squeeze this in here, 25 minus x squared to positive the square root of 25 minus x squared. And then x goes from negative 5 to positive 5, right? Because we want the entire disk, negative 5 to positive 5, right? And bottom to top. So, and then I need a dx in here. So again, probably a doable integral, but probably not that easy, especially with the square roots, right? So it might be more beneficial to convert to cylindrical coordinates, which is, remember, r dz dr d theta. Z, of course, just goes from 0 to 12 again. R goes from, well, here you go, 0 to 5. And theta. So what is theta doing? Theta, this is theta equals 0. We want the entire disks, right? So we have to go all the way around once. So that's just 0 to 2 pi. Okay. So why is this easier? Well, notice that the limits of integration here, these are all just numbers. There's no x's, y's, right? There's no r's, there's no thetas, there's no variables. It's all just numbers. So evaluating these three integrals will be quite simple, as opposed to rectangular coordinates where you have to integrate through by x here on your last integral. And probably using like either a trig substitution or, arc sine or arc secant. I forgot what it was. So probably not as easy. So yeah, let's just do it one by one here. In fact, oh, that's not 25, that's 2 pi. Right. Because the limits here are not, the limits here are just constant. You could literally split this up into 3 separate integrals and just take the product. Again, you have to be very careful about doing this because you really have to make sure that your limits are constants, that they don't depend on, r, theta, or z. Also, that you don't have that your variables here are not mixed, right? So if this is just r, then that's easy. Then the r goes with the middle integral here. But let's suppose you have a function like, 2r squared plus 3rz minus z cosine of theta or something. If that's the function you're integrating here, right? Like if that's the density function or something, now you're probably not going to be able to split it up as the product. So you really have to be careful when you're doing this. To be on the safe side, just don't do it, right? Just do the inside integral first, then the next integral, and then the next, right? But yeah, in this case, the theta integral just gives you 2 pi. This integral is not completely trivial, right? It's 1/2 r squared evaluated between 0 and 5, right? And this is z evaluated between 0 and 12. And so for that reason, maybe let me get rid of the 2 pi here. Oh, let me just cut it out. Doesn't take more than a second here. And then just fill it in. All right, so yeah, so the first integral is just theta evaluated between 0 and 2 pi. Right? So that's where you get 2 pi minus 0. And then this becomes 1/2 5 squared, so 25 over 2. And then there's just becomes 12 minus 0. So you're going to get, what, 12 times 25, which I think is, what, 300 times pi? Yeah, I think that's right, 300 times pi. So that's the volume of this cylinder. And just to confirm that it's exactly as you would have expected, it's just pi times 5 squared times 12, which again, 25 times 12 is 300. So that would have been a lot easier than doing the 3 integrals, but, well, not that much easier, right? Right, so there you go. All right, and if I didn't put in 25, if I just put in, say, capital R squared and then h instead of 12, then doing these integrals here would essentially give you this formula, although I'm using capital R and H for a good reason, because little r is a function. It's the radius, right? It's the distance from the z-axis. And, h, of course, could be either a variable or a constant. All right, so that's our first easy example. I hope this was an easy one, because it doesn't get much easier. Okay, so if we did a cylinder, let's just do a sphere now. Find the volume of the sphere, right? So it's given as a set of points, x squared plus y squared plus z squared is less than or equal to capital R squared. Capital R just being the radius of the sphere. Right. So yeah, don't get confused with the radius of a cylinder. This is the radius of a sphere. All right. The book likes to use A for, say, the radius. That's fine too. I like capital R. Doesn't matter, because we don't use capital R for much else, right? We do use it for like a region in the plane, but that's in that context, it's not a number, right? Here, R represents some number. Okay, yeah, so we could do this. Again, this is the region. Notice I'm not giving bounds here for the other variables, because this is all we need. This is the equation of a ball of radius r. So what's inside the sphere, right? So again, don't get confused, right? The sphere is this, right? X squared plus y squared plus z squared equals r squared, right? That's just the surface, right? So when I said find the volume of a sphere, I guess I misspoke, right? It's the volume of a ball, right? Q is the ball of radius r, and we'll say S is the sphere, which is the boundary of Q, of the ball. Okay. All right, with that out of the way, let's just evaluate the triple integral here, right? So this is the triple integral of over Q of 1 dv. And, right, just to show you what a nightmare this is in spherical coordinates, and we could have done this in the last video, but I didn't really think it's necessary. Maybe it's for homework or something, but, it's a little bit of a challenge. Maybe not much, but a little bit. Yeah, let's get let's get the limits here. So, yeah, so z squared is just going to be r squared minus x squared minus y squared. So we have plus or minus the square root of that, and we really do need the plus or minus in this case, right? Because the plus corresponds to the top half of the sphere, and the minus is the bottom half. At the equator, right, this is where it cuts it off. The plane is z equals 0. So when z is negative, you're below the xy plane, and when z is positive, you're above, right? Okay, so that's the lower surface. This is the upper surface, right? All right, so that's dz. And then what is y doing? Well, if you look at the slice here, this is just the equator. This is just the disk of radius r, right? So this is, x squared plus y squared equals r squared, right? So y is just going to be plus or minus the square root of r squared minus x squared. So negative square root of r squared minus x squared, and positive square root of r squared minus x squared. So that's over y, dy. And then what is x doing? Well, x starts here on the left and goes to the right. So that's just negative r to positive r. Again, if you want a number, these have to be just numbers. And r is representing the number that represents the radius. So that's over x dx. Okay, so this is what it would be in rectangular coordinates, right? And it's not a fun calculation, but it is doable. It's not, if you remember your Calc 2, you should be able to do this, right? And again, the way you do it is just do the inside integral first. And you can see you're going to need some sort of a technique from Calc 2, either by parts or maybe some sort of a trigonometric substitution. So not a fun one, right? But this is why we have spherical coordinates. This is, after all, a sphere, or the inside of a sphere, the ball, right? So what would this be in terms of rho, phi, and theta? Well, if we want the entire sphere, rho has to be less than or equal to r, if we include the boundary, the sphere itself, right? Theta, well, theta goes all the way around. Oh no, theta goes last, right? Yeah, we need phi. So phi is the z-axis here, the angle with the z-axis. So this is 0. This would be pi over 4. This would be pi over 2. But we want to go the entire sphere, the top and bottom. So that's, the straight angle from the positive z-axis to the negative z-axis. That's just pi. So phi goes all the way from 0 to pi. And I was going to do theta, but theta goes all the way around. So that's 0 to 2 pi. Okay, so that's the region Q. That's the ball of radius r in spherical coordinates. So now to do the triple integral, you'll see that, right, you just have to change, you're integrating one, and then you change dz dy dx to rho squared sine phi d rho d phi d theta in that order. Again, there might be instances where you might want to change the order here, but generally not. This is the standard order, just as it was for rectangular coordinates. You like to do dz dy dx. That's the easiest way. So for spherical coordinates, the easiest thing to do is d rho d phi d theta, right? And yeah, you're just integrating one because we're getting a volume here. If we want to get, say, a center of mass, or just to calculate the mass, you have to integrate the density, rho. Now do you see why I like using sigma, right? This is where there's going to be a big conflict. What is rho? This rho is density. This rho is distance. Confusing, right? Because it looks like you're going to multiply rho times rho squared and get rho cubed. But no, they're two different things. So this is why I really don't like the book using rho as the density, because this is density as a function. Okay, so yeah, so this is why I preferred using sigma here for density. There's no conflict with rho. But anyways, we're not doing that here. We're just integrating one. And rho, what is rho doing? Well, it's going from 0 to r. What is phi doing? It's going from 0 to pi. What is theta doing? It's going from 0 to 2 pi. And so this should not be a difficult integral at this point. Let's evaluate it, right? Because we want the volume. So let's do the inside integral first. right? Remember, sine of phi doesn't depend on rho, so that can come outside. We'll do that on the next integral here. So from 0 to pi, we'll do the sine phi. But here, we're just integrating rho squared d rho. Okay, so that's 1/3 rho cubed. I'll take the 1/3 all the way outside. It's just a number. Right. So rho cubed evaluated between 0 and r is just r cubed minus 0 cubed, or just r cubed. Right. Okay, well, that was the first integral. Now we do the second integral, right? The inside integral here. Now remember, r is the radius. R is a number. It's a constant. So if it's all the same, just like with the 1/3, we can bring the r cubed on the outside as well. So far we have r cubed over 3. We're going to go 0 to 2 pi. But we still have to integrate sine of phi d phi. Okay, so yep, we still have to do this integral. But the integral of sine, you should know by now, is negative cosine. Can I just bring out the, well, okay, so here's what I'm going to do. All right, I'll write it as negative cosine of phi between 0 and pi. But there's an awful lot of negatives here, and you can really mess this up if you're not careful. Right? So remember, when you have a negative sign, you can just switch the pi and the 0. So I much prefer to do that. Oops, this is r cubed, not r squared. I prefer to do that. Make this positive cosine phi, and then switch the pi and the 0. Right? You don't have to, but, well, just to show you what this is, right? This is going to be negative cosine of pi minus negative cosine of 0. Now, cosine of pi is negative 1, and cosine of 0 is 1. Minus negative cosine, right, so negative cosine of pi minus a negative, yeah, that's right, I think. Yeah, I think that's it, right? It's negative negative 1, which is 1, plus 1. It's 2. Okay. But here, you're just doing cosine of 0 minus cosine of pi, which is 1 minus negative 1, which is also 2. So here, there's just slightly fewer negative signs, right? Right. Well, half as many. Here, there's 4 negative signs. Here, there's only 2. So either way, you get 2, right? You just get 2. And 2 is a constant. That can come outside. And now we just have the theta integral to do. So you integrate 1 with respect to theta. You get theta evaluated between 0 and 2 pi, which is, of course, just 2 pi minus 0. So 2 times 2 pi is 4 pi r cubed over 3. And that should look familiar, right? This is the volume inside a sphere of radius r. Okay. So yeah, one of the easier ways to actually derive that formula from scratch, right? Again, we could have done this in rectangular coordinates, but that would have been a bit of a hassle, a lot harder than what I did here. Right? And again, to be fair, we could have skipped a lot of steps here. I was, going step by step, so, so I don't lose anyone. If you're wondering how did I get that, hopefully I did this in, in enough detail that you can follow it. But that's it, right? So that's the volume that people say volume of a sphere, but it's really the volume of a ball of radius r. It's the volume inside of a sphere, right? Right. So the sphere itself has surface area, which is 4 pi r squared. And so when we did surface area a couple sections ago, I don't remember if we did this or not. God, that was so long ago. I just keep forgetting. But well, if we didn't do it then, we'll do it we'll do it in a few more sections. In chapter 15, we'll probably do it then. So yeah, that's surface area of a sphere. Here we did volume. All right, yeah, so these two are, again, very easy, as long as you know the conversions, and they're on your formula sheet, but at some point we do them so often that they might become second nature. Okay, so here's one I plucked right out of the book. It's in the exercises, so it could be for homework, but if I remember right, I think it might be one of the even ones. Okay, so it says to convert to cylindrical and to spherical coordinates, right? So we want to do both in this case because it's given in rectangular. So we want to convert from rectangular to cylindrical and then to spherical. And evaluate, we only have to evaluate one of these. I guarantee you, trying to evaluate this in rectangular coordinates will give you a massive headache. I'm getting a headache just looking at it. I don't know how easy or difficult this is, but this is probably not easy at all. So with that in mind, it's probably easier either in cylindrical or spherical. Once we do the conversions, it might be obvious which one we want to evaluate, because it doesn't have to be both, right? So let's start with cylindrical, right? And the integrand here is not 1, right? So we're not getting a volume, right? We're getting, let's say, the mass, right? This could be the density function. I know I'm using rho, but, you know, because we are going to switch to cylindrical, or spherical rather, I'll use sigma again. So the density function is basically just the square root of x squared plus y squared, which you should recognize as just r, right? Little r. Yep, so this integrand here will just be r, right? So dz, dy, dx, remember, will be, how did I want to do this? R dz, dr, d theta, z. Right, so now the hard part, of course, is figuring out the limits. Oh, there's another r here, right? So don't forget, this r is the dv part, and this r comes from the integrand itself. So we're going to end up with r squared here. So I'll leave the two separated for now. Remember, that's dv. Okay, so the hard part, of course, is getting the limits of integration. Okay. Right, and if it helps, you don't have to do this, of course, but sometimes it helps just to write out the region as in terms of r, z, and theta, or I think it's r, theta, and z, right? Yes, r, theta, and z. Right. Well, let's do it in rectangular first, because that's the way it's given, right? So z just goes from 0 to the square root of 16 minus x squared minus y squared. Y goes from 0 to square root of 4 minus x squared, and x goes from 0 to 2. Okay. Oh, so it might be helpful if we actually graph this. Again, maybe you don't have to, but I find it very helpful to draw the picture here. Right, after all, z equals the square root. Once again, this is going to be the sphere of radius 4. So let's do it this way, I think. X, Y, Z. Oh, we got to go in all directions here, I think. So 4 units for the sphere. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then up. 1, 2, 3, 4. Right? This is only the top half of the sphere now, because z is starting at 0. This is the xy plane. Ooh, this might be a bad picture here. I made it a little too tilted. So it should look more like this. So my apologies. Right, and now y is doing what? Y is going from 0 to the square root of 4 minus x squared, which is just the circle. But notice the circle is radius 2 here. So yeah, this is radius 2. And we're only going where y is positive, right? So it's only half the circle, or half the disk. I should call it a disk, not a circle, where y is positive. So that's this disk right here. Okay. And then x is only going from 0 to 2. So now we're down to a quarter of the disk. Right. So this quarter disk right here. Right. So if we extend this up to the surface here, what we're going to get is kind of a cap here, a spherical cap. So this will be spherical up here. And so that's the region. This is the Q, everything in between here. Right. So yeah, can we do this in cylindrical? So r theta and z. Okay, so what's z doing? Z is going from, well, the xy plane is z equals 0. Right? And this is just going to be 16 minus, if you like, x squared plus y squared, which is r squared. Okay. And so in the xy plane, we only need the disk of radius 2. So theta just goes from 0 to pi over 2, right? 90 degrees. And then what is r doing? R is just the radius, right? So we're going from 0 to 2. Yeah, be careful, right? This cylindrical column here, right? This has radius 2. So don't get confused with the radius of the cylinder and the radius of the disk of the sphere, which has radius 4. Okay? So yeah, so little r is the distance from the z-axis, which is 2, not the distance from the origin, which is 4 here. So that's 4, but this distance here is 2. I hope you can see that. Okay, so now we have our limits of integration here, right? So let me go back to this. Z goes from 0 to the square root of 16 minus r squared. R goes from 0 to 2, and theta, wow, I didn't need that much space, right? Theta goes from 0 to pi over 2, not 2 pi. So we didn't need this integral here. Okay, so let me just rewrite it one last time. And we might want to evaluate this. I don't think it's going to be that hard. Oh, I think I changed my mind. I think it might be harder than I thought. Yep, because we're going to get r cubed, and that's not going to be pleasant. Oh well. All right, so before we try to evaluate it, let's now go to spherical coordinates. And yeah, so can we write this in terms of rho, phi, and theta? Phi comes first. So what is rho doing? Well, you might think it's 0 to 4. Unfortunately, that's not how this works, right? So this is the xy plane. Let me do this in blue again. Right, so this is the xy plane. This is the z-axis. And yes, this is the sphere of radius 4. 4. 1, 2, 3, 4. Right? However, we're only looking at the piece above the disk of radius 2 here. In fact, we're only doing a quarter of it. So it's really this piece of it here. Right, so this piece is the spherical. This is just a vertical cylinder. Right? So this is going to be a bit more complicated. Right? Rho will be 4 if I draw these radiuses. So these will all have length 4 up until you get to this radius right here. I messed that up. Let's try to draw it straight. Right? And I know I went too far here, but I'm trying to make a point, right? So this is also 4. But notice what happens after that. If the angle phi here is bigger than this angle, you're not going all the way to the sphere. You're just going to the cylinder. So these lengths here are less than 4. Right? So there's two parts to this. There's the purple part, which is the spherical region. You can think of this as like the, if I do this on this side too, like an ice cream cone, or like a snow cone, I guess. Well, but then you have what's underneath of it, right? That's the green part. So yeah, unfortunately, we need to do both, right? Let's do the purple part first. Rho just goes from 0 to 4, although we know rho is always positive anyway. I'll put the 0 in there. Phi just goes from 0 to whatever the angle this is. So how do we find that angle? Yep, so let me try to draw it over here. You should be able to do this, right? This is the angle we're looking for here or here, right? Obviously, if we can figure out this angle, then just take the complement, take pi over 2 minus a. So phi is just pi over 2 minus a. But either way, right? Yeah, so this distance here we know is 2. That's the radius of the disk, right? R goes from 0 to 2. And we know the radius of the sphere is 4. So if this is the angle we want, forget the a. I thought a might be easier to find. We don't need a here. We just need phi. Right? So it's just trigonometry. It's just trigonometry. Opposite over hypotenuse, right, is sine. So opposite over hypotenuse, 2 over 4 is 1/2. And so phi is the arcsine of 1/2. And the arcsine of 1/2, I believe, is pi over 6, right? 30 degrees. And that looks about right, right? This looks like 30 degrees here, right? From the z-axis, right? Obviously, it's 60 from the xy plane, but that's not how we measure phi. Phi is measured from the positive z-axis downward, right? Okay, so, yep, so this is, we'll just say pi over 6 instead of 30 degrees. And finally, theta, right? Theta is not going from 0 to 2 pi, or even 0 to pi, right? It's the same theta as in cylindrical, right? We're only going a quarter of the disk. So that's pi over 2. Okay. So I'll call this the cone part. But now we also need the green part underneath the cone. And so how do we find Q there? So I'll just call this under the cone. Oh, that's a theta. Yeah. such that what? So what is r doing? Or what is rho doing, right? Rho is the distance from the origin to this, I want to call it a vertical line here, but it's really the cylindrical part of it, right? So how can we represent this vertical line, or this cylindrical side here? Well, this is r equals 2. Right? So now how do we represent r equals 2 in spherical coordinates? Well, either you remember it or you don't, but let's get the picture here, right? So here's phi, here's r, and here's rho, and here's z, although I don't think we need z in this case, right? So if we take the sine of phi, right, we get r over rho, and that was the 2 over 4 we had earlier, but now r and rho could be anything. So r is really just rho times sine of phi. And if r is 2, then rho sine phi is just equal to 2. Right? Which means rho, and I'm running out of space here, if I divide by sine, rho is just 2 divided by sine of phi, or, better yet, 2 times the cosecant of phi. So that's the cylindrical part here, right? That's this vertical line here. This is rho equals 2 cosecant of phi. Right? So rho is going from 0 to 2 times not cosine, cosecant of phi. Yep, that's the hard part, right? You got to remember your conversions and your trigonometry and all that. So, yep, so r is equal to rho sine phi, and if r equals 2, then there you go, right? We just did it. What about phi? What is phi doing? So notice that here we're starting at, right, pi over 6, and we're going all the way down to the xy plane. So we're going, phi starts at pi over 6 here, and then continues on to pi over 2, right, which is just the xy plane. That's your, right, 90 degrees. And theta, well, theta doesn't depend on any of this, right? This is still the quarter disk. So theta is still doing 0 to pi over 2. No different here. Pi over 2. Got it? Right. So, yeah. In cylindrical coordinates, this was just one integral. In spherical, this is going to be 2 separate integrals. Right? So, in other words, to get the, we're not doing volume, right? I forgot this is we're integrating what? We're integrating r here. Or square root of x squared plus y squared, right? So, yeah, so maybe just as a reminder, let's write this out. We're integrating the square root of x squared plus y squared. Originally we had dz, dy, dx. But now we need to write this in terms of rho, phi, and theta. And the way we're going to do it is, right, we're just going to integrate over the cone part plus the underneath the cone. Right? Oh, and don't forget the r in here. Right? Because we're integrating, remember from cylindrical, we need the r, that's the square root of x squared plus y squared, right? Okay, so let's see if we can squeeze this in here. All right, this is not an easy problem. This will take some time to get used to it. All right, so yeah, let's do the cone part first. For the cone, theta comes last, right? So 0 to pi over 2. That's the easy part. Pi over 2, yep. Phi is also just going to be a number, 0 to pi over 6. And then rho just goes from 0 to 4 of r dv. Now remember, dv in spherical, oh, I erased it. It's, yeah, okay. Well, just as a reminder, it's rho squared sine phi d rho, d phi, d theta, right? And to that we'll just add the integral going under the cone. So that's these limits here. Oh, before we do that, hang on a second. The r is not spherical. R is cylindrical, right? There is no r here. So, right, so what do we need to do? We need to rewrite r in terms of, sorry, I'm trying to erase the r here. What is r in terms of cylindrical coordinates? So I just wrote it down earlier, right? Here it is again. Rho is, r is rho sine phi. So this is rho sine phi. Right. It used to be called r, but we have to convert it to rho and phi and theta, right? All right, so now continuing with the underneath the cone parts, pi over 6 to pi over 2, and then rho goes from 0 to 2 cosecant of phi. And again, we're just integrating the same thing here. So rho sine phi, rho squared, sine phi, d rho, d phi, d theta. All right, so I guess I'm just going to write it all over again. Give me a second. Pi over 6, and then 0 to 4. So rho times rho squared is rho cubed, but we also get sine times sine, which is sine squared. Okay, so that's the first set of integrals. Now we have to do this other set. So this is pi over 6 to pi over 2 for phi, and then rho goes from 0 to 2 cosecant of phi, and same integrand, rho cubed sine squared phi, d rho, d phi, d theta. Okay, so I recognize that took quite a while. Maybe I underestimated how difficult this problem was. It's a lot harder than I thought. Right? But now we have two good integrals that we can evaluate. And I think just because this is a single, well, it's a triple integral, right? But it's only one. If we do this in spherical coordinates, we have to integrate both of these. So I'm thinking cylindrical rather than spherical. Because in spherical, we have to evaluate this integral and then this integral essentially separately. Even though the integrand is the same, you might think we can combine them. Notice the limits are very different here. So because of that, they're essentially just two completely separate integrals. Okay. So if we have to evaluate it, and I really didn't want to, but it does say to evaluate, let's just do the cylindrical version and see how we can do that. Okay, so how do we evaluate this? Start on the inside. Right? We'll just evaluate this, and of course this doesn't depend on this is the z integral, right? Doesn't depend on r. We can take the r squared out and integrate the r squared later. So now we're just integrating z, or sorry, we're integrating 1 with respect to z, right? Yeah, so that's just z. Hang on a second. Yep, a lot of writing this down here. So r squared, and then, yeah, z evaluated between 0 and the square root of 16 minus r squared. Okay, so clearly this middle integral here is going to be a little unpleasant because it's not r, it's r squared. If it was just r, in other words, if we just wanted to find the volume rather than integrate the square root of x squared plus y squared, that would have been infinitely easier here. But yeah, because this is r squared and not just r, We need a more advanced technique. It's not just substitution, right? Or maybe it's a trig substitution. Should we try trig substitution? Or by parts? So yeah, my instinct is a trig substitution here. So let's just draw a triangle. Oh, so I don't want to use theta because, well, look, the theta integral is easy, right? You just multiply this by pi over 2. So in the end, you multiply pi over 2 times this integral here. Okay, because none of this depends on theta, right? There's no theta inside here, right? Or the limit doesn't depend on that. It's not 0 to 2 theta, for example. So, okay, so but instead of using theta, I'll still use angle A here. So 16 minus r squared. If this is 4, then this is the square root of 16 minus r squared, right? Yeah, so cosine of A is, oh, we'll use theta. It doesn't matter. I'm just so used to theta here. Okay, so cosine of theta is the square root of 16 minus r squared. So 4 times cosine theta is the square root of 16 minus r squared, right? And then sine of theta is r over 4. So 4 sine theta is r. And then dr will just be 4 times cosine of theta dr. D theta, sorry, not dr. D theta. All right. And if r goes from 0 to 2, sine of theta goes from 0 to 1/2. Right? So I think, don't forget the pi over 2. Let's see, r squared becomes 16 sine squared theta. And the square root of 16, that becomes 4 times cosine of theta. Oh, well, maybe this isn't so bad. And then never mind. Dr is also 4 times cosine theta d theta. So you're going to get cosine squared. And theta is doing what, right? We're going from 0 to the arcsine of 1/2 is again pi over 6. Okay, well, 16 times 4 times 4, it's what, 256? So 256 over 2 is 128 pi. So now we got it down to this integral, sine squared times cosine squared. Well, that does not look a whole lot easier. You know, we did one like this not that long ago where this just ended up just a crazy Calc 2 problem. At this point, if you ever see something like this and you just want to plug it into, your calculator, go right ahead. Right? It'll just give you an approximate answer, but at this point, it didn't say they want the exact, did they? Well, they probably do. All right. Well, so what do we do now? Well, I really just wanted to, just plug this in some computer. So, yeah, it's u is sine. Yeah, that's not going to work. So it looks like what we might want to do is trade cosine squared for 1 minus sine squared. Right. So then we get sine squared minus sine to the 4th, which probably just needs some reduction formula. Okay, so the sine squared, that part we can do pretty easily, right? But it's the sine to the 4th that's unpleasant. to say the least. But yeah, all right. So the first part, the integral of sine squared. Remember how to do that. You divide by 2, and then you integrate 1 minus cosine of 2 theta to the same 0 and pi over 6. So 64 pi. And then here you're just going to get pi over 6. And then when you integrate cosine, you get sine. And then with the substitution, you get 1/2 sine of 2 theta, evaluated between 0 and pi over 6. Right? We'll worry about this one later. Oh, you can already see I'm running out of space here, right? So 64 pi squared over 6 is going to be 32 pi squared over 3. And then minus 32 pi. And then when you plug in pi over 6, you get sine of pi over 3. Sine of pi over 3 is the square root of 3 over 2. When you plug in 0, sine of 0 is 0. So at least for the first integral here, I think we get this much, 32 pi squared over 3, minus 16 pi times the square root of 3. All right, but again, that's only half of it. Now we have to do the integral of sine to the 4th. And since I'm completely exhausted at this point, I'm just going to throw it in a computer and see what it says. Okay, so here's the results. We get pi over 16 minus 7 square root of 3 over 64. Yeah. Okay. Right. If this were sine cubed, I think I gave you the formula for sine cubed on your formula sheet. I should probably do sine to the 4th and cosine to the 4th as well, just so that you don't have to do the reduction formula yourself. Okay, so let's see, 128, it's 2 to the 7 over 2 to the 4, so 2 to the 3 is 8, so this is 8 pi squared, and then minus a negative will be a plus. 128 over 64, I think, is 2, so you're going to get a 14 square root of 3 here. Oh, times pi. Don't forget the pi here. So bringing all this down, so 32 minus 24 is 8, so 8 pi squared over 3 minus 2 pi square root of 3. And I had to check with the book. I think this is correct. So, wow, I'm amazed. I did not expect that to be right after all this. Right. Oh, and so this is the answer to the problem. What was it? Yeah, 8 pi squared over 3. 8 pi squared over 3, and then minus 2 pi squared of 3. Oh, I messed that up, but okay, so that's the integral. There it is way at the bottom here. So it took up the whole screen. And we got it by evaluating what I thought would be the easier one, would be the cylindrical. Remember, we didn't, we could have evaluated both of these, and I'm guessing that this would not be all that much easier. In fact, it probably would be harder. In fact, you're doing it twice. Although the first integral here, to be fair, looks pretty easy. It does involve a sine squared, but we already did that, right? The harder one is the other one here, because this is going to involve some form of cosecant. And so that, I don't know, maybe that cancels some of the sine squared phi, but Not necessarily, or maybe not in the way that I would think. But I don't know. Maybe this way was easier. But, I'm not going to try it because we did it already. We did it using cylindrical coordinates. And so, yeah, maybe spherical would have been easier in terms of evaluating the integral. But that's hard to say. All right, I think we better just end it here. This is about as hard as it's going to get. And I just would not dream of putting this on a test. Something like this. It's a good Calc 2 problem, and it is a good review of Calc 2. We did one like this pretty recently, but trig substitution, partial fractions, these are techniques you should know in case you need them. But in fact, we needed them here. We needed trig substitution here. But overall, now that we can just evaluate these single integrals, the definite integrals using computers, calculators, yeah, feel free to do that. If I ever give you one like that on a test, you have my permission to just throw it in a computer. On the other hand, if you have something like, sine squared theta d theta, I do expect you to work that out by hand. Right? So something like this is not that bad, in my opinion. All right. So I think by doing the sort of the hardest one I could find, hopefully most of the ones in the homework are much easier, and you'll have a much easier time than I had. Because to be fair, I did cheat on this one here. I did the sine to the fourth without using a reduction formula. I just evaluated it on Wolfram alpha. But and if we were going to do that, I should have done it right away. Just throw this in Wolfram alpha, save us all this other work here. But too late. All right. I hope this helps a little. Again, I think the hard part is not really the evaluating. That's not the Calc 2. That's just tedious. The hard part is getting the correct picture here and doing the conversion, right, from rectangular to cylindrical, and then from cylindrical to spherical. Okay, that's probably the part that you want to get most accustomed to here. All right, so I'll let you do that in the homework. Good luck.